Well, good morning, grade 12s. All right, at first I thought maybe I wouldn't make a video today because you've got lots of work to do. Um, However, I kind of changed my mind because I thought maybe we'd do a couple of things tomorrow. Since friction is somewhat of a review, I am going to go in a different order. Okay, so like what I'm going to do today is I'm going to do one thing. We'll talk about friction. We've already talked about friction. Okay, we did that today. Um, or sorry, we did that. I guess you're watching this tomorrow. I'm recording it the night before. So, yeah. So, listen, we talked about friction already. Let's just put it that way. So I'd like to do one thing, just like to review maybe some examples of friction problems. I'm not going to do too many of those because we did do them last year. I have a little assignment for that. And then what I'd like to do is do inclined planes. Okay, so if you look at your course outline here, I'm going in a bit of a different order. So what I'm going to do is I'm going to do this lesson here, okay, friction and inclined planes first. Okay, I'm going to do that first. There are just a few questions from the textbook you could try, okay, right here. Just for extra practice if you like, but I also have a couple of worksheets that I would honestly rather you did those, okay, first. So let's concentrate on the worksheets, okay, for now. So on this lesson here, I do have worksheets for you, okay? And then what I'm gonna do is I'm gonna go back and we will do the pulley systems and so on that you see here, okay, and conservation of string, which is part of doing pulley problems. So pulley problems we'll do separately, okay, and then there's a couple of other things I'd like to talk about too before we get on to circular motion. So we'll get through it, okay. I need to give you time. It's hard to bounce it off. Like the amount of time I give you for problems. I don't want to overwhelm you with too many problems either. So I'm going to cross out a few questions and just sort of concentrate on maybe essential ones that we need to get the concept, and then, for a quiz and stuff like that. Yeah, we should have a quiz pretty soon also on this. So we'll get to that shortly. But anyway, so let's get right to it. So if you look through OneNote, I'm going to keep this short today as well. So guys, there is a friction worksheet here. There's a lot of questions. Now, I just want to go through them, and we'll do them one at a time. And we're not going to go through them, actually do them together, but I'm just going to cross out the questions that aren't really necessary, because there's 13 questions here. You don't need to do them all. So let's cancel a few out. Defining the normal force, you don't need to do that one. So let's cross that one out. Let's cancel number 3. Okay, also, let's just sort of get to the numerical questions. I like the first question though. I do like the first question. So I'm going to leave that one in. Okay. So I will say to do question number 1. So just don't do the ones I'm crossing out. Okay, so number 4 is okay. That's a quick question. Number 5, yeah, I like number 5. It's a good one. It's 2-dimensional problem, so I like that one. It's on the car accelerator. Dash across the dash river. Yes, that's fine. Now, notice the answers are here. Also, these questions were derived from different textbooks, and they reference the textbook. So when you see the word like Cutnell, that's a reference to a textbook. The answer is in bold. Okay, so you'll see the answer there. I'm sure you recognize the numeric. Okay, you can ignore the word that comes before it. All right, so is there anything else? These are pretty quick questions, to be honest with you. Most of them are fairly short. Okay, now a couple of these questions are on slopes. Okay, so these questions here, number 12, number 11, I'm not sure if there's anything else on a slope. I think those are the only 2. So those ones on the slope, you'll be able to do at the end of this lesson, but if you're doing the friction worksheet first and then looking at this lesson, you will have to just wait until after sort of the next thing I teach on inclined planes. I'm going to do that right now, by the way. Okay. All right, so let's talk about something called inclined planes. And this is one of those things in grade 12 that we did not do in grade 11. So far it's been mostly review, okay? So let us talk about inclined planes. And what we mean by inclined planes, I don't know why it's always zoomed out like that. Okay, so what we mean by inclined planes is basically a hill or a ramp, okay? So let's say we have an object like this, and there's a box or something like that resting on an inclined plane, okay? And there's an angle here at the base we call theta. Now that angle of inclination is important because the steeper that angle is, closer to 90 degrees it gets, the more and more acceleration you'll get due to gravity if this object slides down the incline, okay? Now, if we turn this diagram into a free body diagram of the box without having to draw a separate diagram, because I think you get it. Yeah, so it goes something like this. First of all, no surprise to anyone, you're here on planet Earth, there's a force of gravity acting straight down, okay? Now, the other force of the that's on the incline here is a normal force because it's sitting on the surface, right? So that's a surface-to-surface contact with the floor. And that surface contact creates a normal force that pushes perpendicular to the floor itself here, okay, which is inclined. Now, I'm going to try to zoom into this picture a little, and I want to show you something here. I'm going to construct a little sort of imaginary right angle triangle. Okay, so there's a little right angle triangle in here. I'm going to sort of highlight it for you there. That little right angle triangle, I want to point out that this is the right angle. And I'm just going to mark an angle here. That angle at the top we'll call x. Now, x plus theta have to add up to 90 degrees. Okay, and that's because the sum of the interior angles have to add to 180. So that means this angle plus theta, okay, plus 90 have to equal 180. That means that x and theta are complementary, which means they add up to 90 degrees. Now, why is that important? Well, it's important because when we break down inclined plane problems, I was telling my students today, and I will tell cohort A tomorrow in class, when we break down inclined plane problems, we like to tilt our x and y axis so that this is the y-axis and this is the x-axis. And there's an angle here that gravity makes right in here with the y-axis, okay? And what is that angle? Well, here's the deal. See, that y-axis is perpendicular to the incline, and here angle x that you see right there plus this angle here that I've drawn, this missing angle, they have to add to 90 degrees because the y-axis is perpendicular to the incline, okay? So if I were to sort of move that y-axis over here, this angle here, we'll call it, you know, I don't know if you want to call it, no, you know what, we'll just leave it blank there for a second. Anyway, this angle here plus x have to add to 90 just because they form a right angle, right? Now, long story short, I'm going to erase some of this because it's a little messy, not all of that. It's too much. Gosh, my eraser here is very sensitive. Let me try it with this. Okay, let me redraw some of these lines. So here's the force of gravity acting straight down on this. This angle in here we'll call x. Now my point is that this angle here, since x plus that angle add to 90 and x and theta add to 90 in the right angle triangle, therefore this angle must be theta in here. Now that's actually really crucial, okay? So what I've proven, gosh, pardon me that I keep erasing the line by accident. What I've proven here is that this angle here that I'll highlight in yellow, that one there, and this angle here have to be the same angle, okay? Now, you don't have to believe me, okay, whatever. It's geometrically, though, it has to be a fact that those two angles have to be the same. Okay, now I'm going to erase my little yellow highlight there. Now, why is this important? Well, it's gravity that is off the axis. Okay, so remember our y-axis, the normal force is right on the y-axis. So here's our y-axis up here, okay? And the normal force that you see here is actually right on the axis, whereas gravity is not on the axes. It's not on the x or y axis. So this force of gravity down here is off axis. And we always break down our off axis vectors into components. So let me just tell you that Fn is on, there, you know what, I'll make a better arrow. It's on axis, it's on the y-axis to be clear, and Fg is off axis. And it's the off axis vector that we break into components. So I'll use two different colors. That force of gravity has a y component that I colored blue, but it also has an x component down the incline that I'm going to color red. Now the blue one goes with cos because it's adjacent to theta, whereas the red one is going to go with sine. And of course, the vector that we're breaking down is the gravity vector, which is the hypotenuse right here. That vector is the force of gravity, okay? All right, so because this is our free body diagram, now what we're going to do is we're going to go ahead and do step 4 of our method, okay, and break down the vectors by component. So let's take a look at the x component first. And what we'll notice is that there's only one vector in the x direction, and it's this red vector, okay? So the red vector that I drew in the free body diagram is an unbalanced force, and it's in the x direction. So let me, here I'll write it in red so that you get it. The net force, I'll zoom in so it's a little easier for me to write. The net force in the x direction is simply equal to the force of gravity times the sine of theta, and therefore max equals mg sine theta, okay? Now the mass will cancel here, but I'm just gonna leave it like that for now. Remember that the force of gravity is always mg, and that's why I do that substitution. Now in the y direction, let's take a look at our diagram again. There are two forces in the y direction. There's the normal force, which I'll highlight for you here. And then there's also the blue vector, which is the cosine component of gravity. Well, those vectors, pardon me, are equal and opposite, and so they're going to cancel each other out. Okay, now I'm going to write this in blue. And I'm going to treat sort of up and to the right as positive. Up, okay, is plus, is not straight up, okay, the y-axis, but it's up, okay, like so, like, you know, the blue vector, in other words, is going to be negative, whereas the black normal force vector is going to be positive. Now, what we get in the y direction, first of all, there is no y acceleration. Now, this is like, you know, objects are not sinking in or flying off of the hill, okay, in that sort of vertical direction. Now, therefore, we'll make this in blue. The net force in the y direction will equal the normal force, which is on axis and doesn't need to be broken into components. Okay, and then it's going to be minus Fg cos of theta. So, pardon me, MAY equals Fn minus mg cos theta. Now here's the deal, AY is 0. Now that gives us that the normal force now is equal to mg cos of theta. Okay, now that's really all you need to know about inclined planes. Okay, is how you break down the question into components. And so the secret to solving inclined plane problems is tilting your x and y axis so that we have an x-axis that is parallel to slope, and the y-axis is perpendicular to the slope. Okay, so you tilt your x and y axis, and then you just break it down as usual into components, right? And that's how you do inclined plane problems. It's very simple, actually. Okay, so keep this in mind. And when we go to look at the inclined plane worksheet, okay, I just want to point out a couple of things. Number one, okay, when they say a truck is 562 newtons, what they mean is that's the force of gravity on the truck, okay? In other words, that is equal to mg, okay? That is the force of gravity on the truck, okay? And that's equal to mg. Now, this is important because when you're working out the components, and by the way, I posted the answers here in the margin, but when you're working out the components, you're going to need, you don't need the mass, but you do need to know what m times g is. Okay, so in other words, you need the weight of the truck. Okay, so let's go ahead. I'm going to do number one with you. I'll show you how easy it is. Pardon me. Oh. So they say here the angle of the incline is 30 degrees. Now that's always measured at the base. So we can draw the free body diagram one more time. Okay, so here's my free body diagram. Now it says the 562 Newton truck, my free body diagram, it's on a 30-degree frictionless incline, so there's gravity, there is a normal force, and then there is an acceleration in the x direction down the incline. And it, of course, is gravity that we're going to break into two components because it's off my x and y axis. And I should say that this is our unknown that they're looking for in the first question, find the acceleration of the truck. And of course, AY is always 0 on an inclined plane. So this is question number one. All right, so now here's the deal. Let's just look at the X components because we don't actually care about the Y component right now in this question, okay? So the X component just goes like this. I'm getting ahead of myself. F net equals force of gravity, force of gravity times the sine of 30 degrees. Now, like I said before, the value of theta will fit in the triangle here. Okay, the value of theta that they're telling you about the incline, that's where it gets translated up into our vector diagram. And so we'll use sine and cos of that. So here's the sine component, which is the red vector that you see here. So MAX will equal mg sine 30. I'm going to cancel out the m's because after all, we actually have to figure out what m is because they didn't tell us. They only told us the weight, which is mg. So we can work out the mass. But anyway, here we go. So we get ax is equal to g sine 30. Now, if you put in 4.9 for g, that number's, sorry, not 4.9, 9.8 for g, then you get the answer is 4.9 meters per second squared. Okay, so it's going to slide down the hill at 4.9 meters per second squared. So there's your answer for question one. Of course, we knew that already. It's right there, so we got it right. So check. Okay. Now, the second half of this question is actually trickier than it sounds. It says, find the acceleration if the coefficient of friction was 0.3. Now, they mean kinetic friction, if it's sliding down with some kinetic friction. Now, if there is kinetic friction always opposes, it's this type of skidding, and it will always oppose the motion. So my frictional force, which I will color red again, will actually go up the incline like that, and that is your force of friction. So now what the force of friction does is it introduces another on-axis vector. This one is on the x-axis. So we don't have to break it into components. But when we're doing question B, watch what happens here when I factor in force of friction. So my net force, I'm still going to make down the hill positive. So it's going to be the force of gravity times the sine of 30. And then I'm going to subtract the force of friction this time. So see the difference between what I wrote here and what you write when there's friction involved. Okay? Now, the formula for friction is that the coefficient of, oh, pardon me, putting text all over the place. The coefficient being 0.3 in the question, okay, that's the coefficient of friction, in this case, sliding friction. So therefore, the force of friction equals mu, hard time writing, mu Fn. That's the formula that we always use for friction. So you see here, we have a separate issue that we need to work out. What we need to work out is what the normal force is. So they told us the coefficient is 0.3 in the question. Now it's our job to work out, pardon me, the normal force. Well, the normal force, okay, on this object, see, because it's on an incline, we actually have to look at the other component, okay? So when we look at our y components, we're going to get the net force is equal to the normal force. And see, we need the normal force, right? And then that's going to be minus the force of gravity times the cos of 30 degrees. Well, they told us the force of gravity was 562, pardon me, newtons. Now that's already mg. That's actually the force of gravity on the object. So this is 562 newtons. I'm not going to solve it for mass. I'm not going to put mg in there, but I am going to put may. May equals Fn minus 562 times the cos of 30. Now we know ay is 0. So that term is 0. So therefore the normal force is equal to 562 times the cos of 30. And that's just a number, right, that you can enter into your calculator. Well, now we get back to our original question. Now that we know what the normal force is, so that's just a number, now we can find the friction. So therefore, the force of friction will equal 0.3 Fn. And then you get to substitute in for Fn what it is, okay, what we just worked out. All right, so now that we've worked out how much friction there is, now we can go back to our question, our solution, and say, okay, so the net force is equal to mg sine 30. Now we know this is 562. The whole expression, both the m and the g disappear when you put that in. And then it's going to be minus whatever you get, okay, here for the force of friction. So whatever that force of friction is, plug it in there. So it's going to be minus the force of friction. And just go ahead and plug in the number that you got for the force of friction. Okay, so now we replace the net force with ma, and there you go. You can solve it for the rest, and I'll leave it to you. All right, so that's how you do an inclined plane problem with friction. You just break it into components. Now, we've been working on components, and hopefully it's generalized enough in your head that you'll be able to figure that out, okay, when you're doing an inclined plane problem. All right, so anyway, your worksheet includes the friction worksheet, and we crossed out a few of those. So I know I only crossed out 2. But now you know how to deal with inclined planes, like as promised, these 2 questions, inclined planes with friction. Okay, with or without friction, it doesn't really matter. I think they both have friction. So have a good day, cohort B. I will see you soon, and soon we'll also have a quiz at some point just to see if we can quiz you on a few of these questions. I like having little quizzes instead of long tests. I think during the pandemic it helps for you. Focus on one thing just for a short time. And that's it, guys. So have a great day, and I will talk to you soon. Don't forget, if you need help, just ask. Okay, talk to you soon.